Data quality can be assessed using many commercial and open source tools. In a previous video, we used the White Rabbit open source tool supported by the Observational Health Data Sciences and Informatics, or Odyssey community. In this video, we dig a bit deeper than can be done using that tool. For this video, we will use raw SQL directly against the Mimic database. Data quality measures can also be calculated in a variety of programming languages, such as R and Python. Briefly, here are the definitions of data quality dimensions, data quality measures, and data quality rules. In this video, we focus on quantitative data quality measures. Because data profiling is a common basic task, there is a huge commercial open source marketplace for data profiling tools. Google Cloud Platform, which is our technology partner for this class, has an integrated tool called Data Prep that focuses exclusively on this task. Unfortunately, at this time, Data Prep is only available in the United States and therefore is not used in this module. For this video, we will use SQL to calculate quantitative measures for data quality. SQL is a powerful generalized data querying language. We are going to focus on relatively simple quantitative measures. To assess continuous data distributions, we'll use the SQL standard aggregate functions mean, min, and max. While median is available in some SQL syntaxes, it is not available in all SQL variants, so we will not use it in our examples. To assess discrete categorical data distributions, we will use simple value-based histograms. For temporal density, we will use simple annual rates. Using the full power of SQL, it is possible to calculate a much wider range of complex quantitative data quality measures. In examining the Mimic tables, one does not find many variables that are intrinsically continuous variables. Most variables in Mimic are discrete categorical variables, but we can create continuous variables from existing Mimic variables. For example, we will compute the number of days a patient was in the hospital, called length of stay, which is the number of days between when a patient was admitted and discharged. One surprising controversy over calculating length of stay is what value to give when a patient is released on the same day they were admitted. Is that 0 days or 1 day in the hospital? There actually isn't a best answer, but just for simplicity, we will use 0-day counting. Others may use 1-day counting, which simply requires adding a +1 to the end of our dateDiff function. For these examples, we will move over to using the OMOP version of the 100-patient Mimic database. In OMOP, information about hospital stays are stored in the visit occurrence table. Admitted dates are stored in the visit start date, and discharge dates are stored in the visit end date. Most SQL dialects, including Google BigQuery, provide a time difference function called dateDiff. The syntax for dateDiff can be found in BigQuery's online SQL documentation. dateDiff has 3 arguments: the ending date, the starting date, and the time interval, or chrono. In our example, the chrono we will use is day. In subsequent slides, we will abbreviate the dateDiff statement with the string LOS. To actually execute these statements, replace the LOS string with the dateDiff command shown here. Length of stay is a continuous variable that should range between 0 and a reasonable positive number of days. A negative number would suggest a data quality issue, since this only happens if a patient is discharged before they have been admitted, a clearly nonsensical situation. Here is the actual SQL statement for calculating the minimum, maximum, and average length of stay against the OMOP version of the demo MIMIC database. Fortunately, there are no negative length of stays. A reasonable next query would be to create a histogram of the number of patients who had a length of stay equal to 0 days, 1 day, 2 days, 3 days, etc. We use a simpler example to create a similar histogram. In a previous video using the White Rabbit profiling tool, we showed the distribution of ICD-9 code values in the MIMIC diagnosis ICD table. We now show a similar analysis of the distribution of diagnoses using the OMOP version of MIMIC. Diagnoses are stored in the condition occurrence table in OMOP. The code for a diagnosis is found in the condition concept ID field. Here, we show the SQL statement that counts the number of diagnoses found in the condition occurrence table, grouped by each value of condition concept ID. I have added the order by descending clause at the end so that we can see diagnoses starting with the most common ones first. The output from the previous query showed that condition concept ID equal to 0, which means that the ETL code did not find a matching OMOP code, is the highest condition concept ID. This is an unexpected finding that needs more investigation, since OMOP has an extensive vocabulary for ICD-9 codes. That is, there should not be any ICD-9 code in MIMIC that doesn't have an OMOP code, yet this analysis is saying otherwise. After 0, the next most common diagnosis is 132797, followed by 320128. We are seeing the same issue here that we saw using White Rabbit on the MIMIC database. What diagnosis is represented by condition concept ID 132797 or 320128? In White Rabbit, we had no way to automatically decode the code into a human understandable text string. We had to do a separate query. But in SQL, we can do the necessary joins to replace the not meaningful condition concept ID with a meaningful condition code string field. OMOP contains a single dictionary table that converts any concept ID into a human readable string. The concept name field holds those text strings. By adding a join clause to link condition concept ID to the concept ID in the OMOP concept table, we can replace the numeric concept ID with the concept code string. This expanded SQL statement that includes the join between condition occurrence table and the concept table highlighted in yellow. The select clause will return not only the numeric condition concept ID as before, but now will include the concept name. We see the expanded results here. While nothing has changed in terms of the ordering of diagnoses, we now have the concept name column to decode the condition concept value. We now see that no matching concept is most prevalent, followed by the diagnosis of sepsis, essential hypertension, and atrial fibrillation. In looking at the top diagnoses, MIMIC clearly represents an ICU population, since many of the top diagnoses are extremely life-threatening. One interesting side note from our previous query: our 100-patient MIMIC demo database returned 546 different diagnoses. That is, on average, each person had 5 to 6 diagnoses per hospitalizations. Again, confirmation that mimic population is unusually sick, which aligns with its origins in ICU patients. As our final example using SQL, we look at a simple temporal density measurement, the number of hospitalizations that occur per year in MIMIC. In OMOP, hospital admissions are stored in the visit occurrence table. We will use the visit start date column for the year of admission. To extract just the year value from a date field in BigQuery, we will use the extract function. This is the SQL query that provides the number of admissions per year. The components of the extract function that provides the year are highlighted in yellow. The query includes an order by clause that will list the years from earliest to latest. This is the result of the annual admissions query. Notice that the dates are all in the future and are widely scattered. This is the result of the annual admissions query. Notice that the dates are all in the future and are widely scattered. This results in a histogram where each year only has a small number of admissions. Neither the values for year nor the number of patients per year make sense. This requires further investigation as part of our data quality analysis. Specialized tools or programming languages are needed to dig deeply into the database or data sets to calculate more complex data quality measures that reveal subtle data quality issues. SQL is just one language that can be used to go beyond measures available in data profiling tools. Different types of data quality measures apply to different data types. We showed simple examples for continuous, categorical, and temporal data elements. While SQL can help calculate more sophisticated data quality measures, it is unable to help with visualizing the findings that could reveal non-obvious patterns, or for applying data quality rules that can assess if the available data quality is acceptable for an intended use case. For these features, we need an environment dedicated to supporting data quality. We highlight one such environment in a subsequent video in this module.